So, physical intelligence just rolled out Pi 0.5, and the big idea is surprisingly down to earth. Spread the brains of a robot everywhere instead of parking them in one central processor. Each finger pad, elbow joint, even a patch of soft silicone gets a tiny slice of neural smarts that can sense, decide, and adjust on the spot. The result is a machine that walks into a new apartment, notices where the dishes pile up, and starts sorting them without needing a map or a Wi-Fi lifeline. It's more like a crew of quick-thinking muscles than a single slow command center. Exactly the sort of step you need if you want robots to feel at home outside carefully scripted labs. Now, here's the twist. Pi 0.5 isn't one single gadget or one single neural network. It's two layers that share a name but tackle totally different headaches. Think of the lower layer as robot reflexes and the upper layer as robot common sense. Let's start at the bottom. Traditional robots pipe every sensor tick back to one chunky processor, do a bunch of math, then shout motor commands to the limbs. Works great on a factory line where nothing changes. But drop that same bot into your cluttered living room and latency, power drain, and plain old confusion hit like a brick. Physical intelligence flips the script with Pi nodes. Imagine little Lego blocks distributed all over the robot, one inside each finger pad, a couple in the elbow joint, maybe one tucked into a soft silicone palm. Each node has its own tiny sensor rig, its own actuator hookup, and a mini neural network that runs a lightning-fast reinforcement update rule after every micro move. The node basically asks, did that reduce slip? Did that ease tension? And tweaks its weights on the fly. Because the brain is smeared out across dozens of nodes, they don't need to ping a central server. That cuts communication chatter and slashes power. In physical intelligence's test with a soft robotic gripper, those local reflex loops bumped grip accuracy 30% and trimmed power draw 25% compared to the old phone home architecture. Same story on a wearable haptic sleeve. Smoother feedback, longer battery life, zero hand cramp. And they baked in proprioceptive and tactile sensing, so if the gripper bends or stretches under load, the node compensates before the slip even shows up on camera. Hardware agnostic too. Stick the firmware on an ESP32 if that's all you've got. Alright, that's reflexes. But reflexes alone don't tell the bot whether the thing it's squeezing is a sponge or a steak knife. Enter the upper layer, also christened Pi 0.5, but formerly a Vision Language Action Model or VLA. If you've tracked AI the past couple of years, you know the drill. Pour mountains of captioned images and language data into a transformer, fine-tune on robot demos, and pray it generalizes. Most groups nail cool stunts on the exact table they trained on, then fall apart in a new room. Physical intelligence took the generalization problem personally, so they went absolutely wild on data diversity. Step 1. Record about 400 hours of mobile manipulation footage. Robots cruising real houses, knocking into chairs, figuring out panhandles. Step 2. Add static robot clips shot in dozens more environments, then toss in cross-embodiment data from simpler arms that don't even have wheels. Step 3. Mix in standard web soup captioning, VQA, object detection, plus verbal instruction sessions where a human literally coaches the robot through complex chores step by step. The result is a Frankenstein curriculum that teaches Pi 0.5 everything from what's a pillow to how hard can I squeeze a ceramic plate. Did the smorgasbord pay off? They ran 2 gauntlets. First, in distribution cleaning tasks. Basically, homes similar to places in the training set. Pi 0.5 pulled an 86% language following rate and 83% task success across nitpicky subtasks, like every single dish making the hop into the sink. Then they cranked up the heat, and out of distribution test where the house, the objects, even the lighting were brand new. Full Pi 0.5 still nailed 94%, both on obeying the prompt and finishing the job. Cut the internet photos from training, and those numbers dropped to mid-70s. Yank the multi-environment robot data, and success cratered to 31%. So yeah, variety isn't just spice, it's oxygen. They also did a scaling study, dialing the number of distinct training houses from single digits up to north of 100. Performance rose almost linearly, and after roughly that 100 home milestone, Pi 0.5 basically tied a cheating baseline that had seen the test houses during training. That's insane. With enough diversity, you get home field advantage without ever stepping on the field. Here's my favorite engineering nugget. When Pi 0.5 is live, it goes through a legit chain of thought loop every second. First, it spits out a high-level text thought like pick up the pillow, using discrete token decoding the same way ChatGPT writes sentences. Then, no model swap. It slides those weights into a continuous flow matching head that produces 50 joint angles, a 1-second action chunk. Boom! The arm moves, the nodes micro-adjust grip, the camera snaps a fresh frame, and the process repeats. One shared brain. Language and talk fused, moving in real time. And because the lower-level node reflexes are so fast, the VA can afford to think at a slightly more contemplative cadence. It plans the next semantic move while the fingers keep the plate stable. That separation mirrors how your spinal cord handles a coffee cup's weight, while your prefrontal cortex wonders where you left your keys. They stress-tested the whole stack in actual strangers' apartments. No pre-scanning, no fiducial markers, shooting videos of successes and goofs alike. The bot makes beds, folds laundry, scrubs spills with a sponge, scoops up toys. Sometimes it misidentifies a plushie, sometimes the arm trajectory drifts, but it often recovers. They even had bystanders bump the arm mid-wipe just to see if it freaks out. Mostly, it recomputes and keeps wiping. You can yell precise commands like pick up the round brush and it targets the exact object. Or stay vague with clean the bedroom and watch it break the mission down into bite-sized subtasks all by itself. From a battery standpoint, the decentralization story is gold. Each node only spins the math cores it needs so the mobile base can roam longer before docking. That's why the Gripper demo posted a quarterless energy draw. And remember, those nodes run on microcontrollers. You can power off a coin cell if you want. Edge intelligence for the win. On the math side, the flow matching sampler in the continuous head is clutch. Diffusion models typically need dozens of steps, but flow matching can pop out a trajectory in a single forward pass. Crucial when you have maybe 20 milliseconds between sensor read and motor pulse. They cap action chunks at 50 steps because 1 second balances servo refresh rates and mood swings in the high-level planner. Long enough to finish a swing, short enough to pivot if something unexpected happens. So where do they go from here? The team is blunt. Pi 0.5 still whiffs it sometimes, chooses the wrong high-level plan, bumps a cabinet, grabs a fork upside down. They're dreaming of models that learn from their own runs without human labels, ask clarifying questions on the fly, and transfer skills between wildly different hardware. Picture the same brain swapping from a 2-arm mobile base to a wearable exo sleeve without retraining. They're also begging for partners who operate fleets in grocery stores, hospitals, elder care homes, any place messy enough to feed the data monster. Let's circle back to that house party fantasy. The secret sauce is really twofold. First, intelligence embedded in the body, the Pi nodes. That means your robot isn't waiting for a Wi-Fi round trip to figure out it's crushing a tomato. Second, a monster VLA that's seen enough homes, frames, language instructions, and cross-route demos that it can walk into yours and not freeze. Those layers together blur the line between trained routine and genuine adaptability. So every second, the robot is holding a silent conversation with itself. Okay, the high-level goal is to wash dishes. First sub-step, pick up the spoon by the handle. Nodes, give me 3 newtons of grip and watch for slip. Good. Now rotate toward the sink. It's a chain of thought with a proprioceptive heartbeat, and that's why this drop matters. For years we've had bots that can stick the backflip landing, but only on their native mat, or language models that can talk your ear off but can't twist a doorknob. Pi 0.5 stitches the two sides, not by chasing an ever bigger centralized model, but by marrying edge reflexes to a data-rich caretaker brain. It looks like a midpoint, as the name hints, halfway between the first Pi 0 and whatever Pi 1 mega brain might be. but halfway already gets you a robot that can enter a brand new kitchen, spot unseen plates, plan a cleanup, and crucially, tighten or loosen its grip in under 10 milliseconds without sipping too much battery. If that's half the journey, the next half is going to be wild. Alright, now what real-world chore would you trust a Pi 0.5 powered robot to tackle first? If you enjoyed the breakdown, tap that like button and hit subscribe so you don't miss the next deep dive. Thanks for watching, and I'll catch you in the next one.